Hi, welcome to my presentation on Bayesian statistics. My name is Johnny Wu. I'm a pharmacist. I used to work at University Hospital, was there for about 7 years on medicine team 3. Currently at Milton District Hospital, although I still work at University Hospital at the capacity of relief pharmacists when they're desperate enough to take anybody. You might see me there in the summer, but otherwise I might see you around in the GTA. So the primary goal of my presentation is that after this presentation, you'll be able to list 3 reasons why researchers and clinicians might want to use Bayesian statistics. You'll be able to describe and explain why Bayesian statistics is not used as often as its more familiar counterpart, frequency statistics. You'll be able to describe what a Bayesian prior is and what kind of information and process goes into creating the Bayesian prior. You'll also learn what BFF stands for. But I don't know about you guys, but a lot of people find statistics to be very dry. And even in the best of times with frequency statistics, where the concepts involved are introduced again and again and again, you encounter it in papers that you read, you encounter it in the practical labs that you might have in biochemistry. It's still very confusing, and if when you read the results section of a paper, it tends to be very dry. You kind of roll your eyes and have to refocus on what you're reading all the time. So I assume that this is more of the same with Bayesian statistics, compounded with the fact that a lot of these concepts will be entirely new to you. You wouldn't have had the benefit of being reintroduced over and over again during your formal education. And so you can rest assured that there is probably a very slim chance that you'll probably end up using these concepts in your career. So I just want you to know that Bayesian statistics it exists. It's important in its own niche, and by introducing concepts to you, maybe by the next time you hear these concepts, it will seem a little bit more familiar, and over time you'll be able to understand it a little bit more and more and more, and then you might end up using it. So this graph is the number of papers in medicine that have used Bayesian statistics as its main method of testing its hypothesis. As you can tell, this is an exponential curve. When I started my career, Bayesian statistics, no one ever really mentioned it, but now it is mentioned often enough that Chris asked me to come back to explain this to you guys. And there are many reasons why has been a very slow ramp up of the use of Bayesian statistics. And I'll go into greater detail in later on in my presentation. But the gist of it is that Bayesian statistics requires computational power, which wasn't really available until the 1980s. And by then, practice in the field of statistics and in the field of medicine have already been entrenched, and formal education reflected those practices, and so there was a lot of momentum to get it started. But as you can tell, the rise is exponential, and actually it is thought in the year 2050, the number of papers published with Bayesian statistics is going to be so high, the Earth is going to be 3 meters deep in Bayesian papers. Okay, let's start with a practical example. So let's say we have an RCT and a new lipid-lowering drug. Okay, so there's very small sample size. Okay, let's pretend it's a phase 2 trial. So control, you have 10 people. Intervention, you have 10 people. And then what you do is the beginning of the trial, you measure their LDL, and then they take the placebo, or they take the intervention for a year, and then after a year, you measure their LDL again. And so this is the result that we get. We assume a normal distribution, and we have a mean change in the LDL of 0.5 for the control. So we have a slight decrease in the LDL. Intervention, you have a greater decrease. But if you look at the standard deviations of the change, there is quite a bit of overlap between these two curves. So you can't tell by looking at it whether or not you have a significant decrease in the LDL. So we don't really know whether or not this lipid-lowering drug really works. So how do we do this? Well, we do statistical tests to answer the question. What is the question? How do you phrase the question? So what is the is it question A? What is the probability that the drug decreases the LDL given our data? Or is it B? What is the probability of the data assuming there is no difference? I mean, in these presentations, whenever there is a multiple choice question, it's often the answer is the most ridiculous one because that is the most catchy, and in the case it's true. So A, which is I think what is, if you were to speak colloquially about what you're trying to do with a study, it would be question A. You're testing the hypothesis. Whereas B, not only you're not testing hypothesis, you're testing the data, and then you're making assumptions, and the assumption is different than the one what you truly expect. You wouldn't hold the study if you expected there was no difference. But B is what we do in practice. We test the probability that the data arises assuming a null hypothesis, and if the probability is low, then we reject the null hypothesis. When you start learning about this process, it will seem just almost like a very archaic, song and dance, horse and pony show kind of thing. Like, why would you create a null hypothesis and then reject it later? It just all seems like a needless formality. But this is necessary because of the limits of frequentist statistics. So what is the difference between frequentist statistics and Bayesianism? So as it relates to the hypothetical study, the frequentist tests the probability that the null hypothesis produces the data, and if the probability is lower than some threshold, so we usually choose that to be 5%, and also do we accept a 5% rate of a false positive, then your trial reached its goal, and otherwise you have to accept the null hypothesis. But what Bayesian statistics does is it tests the probability that the two populations are different. They're a direct test of the probability. I want to mention that frequentism might be a new word to you, but frequentism encompasses nearly all the statistics that you've learned so far in your education, unless the statistics class or lecture, whatever, has explicitly said it is Bayesian statistics. So by default, most of the stats that you have learned will have been frequentist statistics. So, chi-square test, p-values, confidence intervals, t-test, ANOVA, et cetera, et cetera, et cetera. Everything is frequentism. So why do we use frequentism? It's because it's easy to understand. It's easy to understand mostly, I believe, because that is what we're taught in school, and we're taught it over and over and over again. They breed familiarity. So when I took stats, the stats that was very mathematically involved, and I have very little talent in math, but I was able to do a lot of the proofs because the math behind frequentism is very, very simple, and that's part of the reasons why it became entrenched. Frequentism is unbiased. You don't have any assumptions about the data before you do your statistical analysis. And this can be an advantage in science when you want to come in with an open mind. And likewise, because unbiased, you don't have to have any prior knowledge of the data. You don't have to make any assumptions about what kind of distribution it is going to have or anything like that. it's easy to compute. You can do it with a pencil and paper if you are so inclined. So people did frequentist statistics back in the 1920s before computers. And you can still do that now. And it's nearly universal in medicine. So some of the cons is that it has subjective alpha. So alpha is the p-value threshold that you must cross, and there's a law called Goodhart's law. Goodhart was an economist. That when your measure becomes a target, it ceases to be a good measure. If your livelihood and your dignity is dependent on you having a p-value less than 0.05, then you might be very inclined to make sure that happens. And this is called p-hacking. It's a problem in literature. And so then p-values become less and less important because of this. The other downside is that you can only reject the null hypothesis, or you'll have to be, or you just have to accept the null hypothesis, but you don't generate any alternative hypothesis. So just because so let's say going back to our study, you have a decrease of like 0.5 millimole per liter of LDL. If you find that the p-value is less than 0.05, you reject the null hypothesis, but you don't accept the hypothesis that the difference is 0.5. All you can do is say that the difference between two populations are different. It doesn't tell you by how much. It doesn't tell you how confident you are, but that you're separated by how much. Similarly, it does not provide any confidence that the null hypothesis is true. You kind of accept the null hypothesis by default, but there is no gradient. There is no level of certainty that you know that the null hypothesis is true. And lastly, the frequentist statistics simply does not work well on a small sample size. It works great on a large sample size, and some say it would be ideal for studies that are well conducted and have thousands of patients, and that's why you see charts where you have different kind of lipid lowering agents, and then you have how much how low or how well the lipid lowering agent works. These are alternate hypotheses, but they kind of work because they're very large cardiology trials, right? There's thousands of patients, and you can get the kind of power that you can make these assumptions. But that doesn't work with small sample sizes. So people use, in contrast to frequentist statistics, people use Bayesian statistics because in some ways it is more intuitive. It directly answers the question that you would pose, as opposed to going about it a roundabout way. It generates alternate hypotheses. You don't have to just accept or reject a null hypothesis. And the most important thing is that it elegantly incorporates prior information. This is in contrast to frequentist statistics. As I've mentioned before, it is unbiased. So in some ways, I guess you could say that Bayesian statistics is biased, therefore it is fundamentally flawed for the use in scientific enterprise or whatever. But I would say that is probably not the case. We all use prior information in one way or another, and Bayesian statistics allow us a formal process to incorporate all the prior information that is available to us to interpret new information. And the pro is that you can deal with very small sample sizes. So the con is that it is difficult to compute. It's very difficult to do it by hand. There are analytical solutions to the Bayes formula. So analytical solution means that you use a calculus, and then you pencil and paper, and then you solve it using like integrals, et cetera, et cetera. So there are ways to solve it using that method, but those problems that it solves tend to be more theoretical than they are practical. And in order for a practical problem to be solved, you really need a computer. These computers run something you might be familiar with. They're called Monte Carlo simulations, Markov chain Monte Carlo simulations, and they use something called the Metropolis Hastings algorithm to solve a Bayesian problem. And you can't really do that by hand. You really need a computer to do it. And a lot of lay clinicians don't really understand papers that use Bayesian statistics, mostly because they are they're not exposed to it as often as they are exposed to frequentist statistics. And one other con is that with Bayesian statistics, often you need to formulate a subjective prior. So you can have an objective prior using prior empiric data, but one of the advantages of Bayesian statistics that is sometimes employed is they use a subjective prior. So the following is a table of the difference between frequentist and Bayesian statistics. So in frequentist statistics, it's asked whether or not the null hypothesis can be rejected, whereas in Bayesian statistics, you ask what is the probability of the hypothesis given the data. At the end of a frequentist analysis, you would get a point estimate. In this case, of course, you can get constant error, but in this case, we get a p-value. At the end of a Bayesian analysis, you would get a curve. You would get a posterior distribution. I'll talk a little bit more about that later. You'll get a posterior distribution that describes the probability for or against the hypothesis. The main advantage of frequentist statistics is that it is simple to use, widely accepted, whereas for Bayesianism, you can incorporate prior beliefs, and it informs a greater degree of certainty or uncertainty. It is not just a dichotomous result of true or false, reject, accept. With frequentist statistics, they're great when you have large data sets. In contrast with Bayesian statistics, it is best when you have limited data or when you have priors that you want to incorporate in your analysis. So I talked a lot about Bayesian statistics, but you might not even know what is it, like what do you do? What is the nuts and bolts of this method that you spent 20 minutes talking about? Bayesian statistics is this is the Bayes formula. This is Thomas Bayes. He was a minister, and he published a book on conditional probabilities. He actually did not devise the Bayes formula. It was actually done a few decades later by another statistician. So this is the Bayes formula. It's the probability of A given B is equal to the probability of B given A times the probability of A divided over the probability of B. Very, very elegant. So what you're trying to solve is the posterior distribution, and in order to solve it, you multiply the likelihood. The likelihood is, by the way, for our purpose, tends to be data, so the data that you collect for your study. And you multiply that by the prior, and the prior is your prior understanding of the data before you even collect the data, and then you divide it by the marginal probability. Now, the marginal probability is often either difficult to get or just completely unattainable, and that is why we need computers to do it. Because with computers, you bypass calculating the marginal probability entirely. So oftentimes when you're teaching Bayesian statistics, you'll give a much more easy to understand concept as opposed to just letters A and B. So an example that is sometimes used is what is the probability of rain if it's windy and cloudy? It is a probability that it is windy and cloudy given that it's raining, multiplied by the probability that it's raining, divided by the probability that is windy. Okay, let's start with an example of the application of Bayesian theory in a more familiar space and something that you will be able to recognize. So let's say we have a COVID test, and this COVID test has a sensitivity of 50%. And what that means that you know that the patient has COVID, and 50% of them, if you test them, will be positive, whereas the test will be negative for these COVID positive patients in 50% of the time. This is not a good test, of course. Real COVID tests are much more sensitive, but for this hypothetical situation, let's say that this COVID test has a sensitivity of 50%, but it conversely has a high specificity of, let's say, 95%. And in this hypothetical situation, in a hypothetical world, let's say a patient comes in with COVID-like symptoms and you swab them, the test is positive. What is the probability that the patient has COVID? Remember that the sensitivity was a ludicrous 50% and the specificity is 95%. What is often guessed is that it is because the sensitivity is 50%, then the probability that the patient is COVID positive is 50%. But this is actually incorrect. It actually depends. It depends a lot on the context. So back in March 2020, everyone in the ER had COVID. If you didn't have COVID, you weren't there. So the rate that the probability that the patient has COVID, if you give the test, actually does not depend on the test at all because they were all positive. Let's say if you took the test into a time machine and you tested a patient in the ER in 2019, and you did that instead of warning people about COVID. But anyway, so what you decided to do is just use a test on somebody in 2019. Nobody had COVID back then. So the test would obviously be negative regardless of what the result was because the rate was zero. And another example is what if it's medicine at UH? The medicine floor at UH has the highest rate of COVID patients in the world, perhaps the universe. So everyone there is going to be COVID positive. In contrast to Sentinel Island, where the residents of Sentinel Island had to go all stabby on the kind of visitors that visit the island. Their COVID rates are, I'm going to guess, they're probably zero. So whether or not a patient has COVID given a positive test depends a lot on the rate of COVID itself. It is called the pre-test probability, the probability that they have it before you even test them. And we learn a lot about sensitivity and specificity in class, but those numbers are used when you know the disease state and you want to find out how accurate your test is. When you're a clinician, you don't really care about the assay. You don't care about the test. What you really care about is the patient. Does the patient have the disease or does they not have the disease? And you do that by doing a test. And if you have the result of the test and you want to figure out the state of the disease, what you're looking for is the positive predictive value and the negative predictive value. They're sometimes abbreviated as PPV and NPV. This is a figure that you'll probably see many times in your career. So I'm just going to briefly show you that the sensitivity and specificity are related. They're on the same figure, but depending on what your goal is and whether or not you want to figure out the properties of the test or the property of the patient, you're going to use different numbers. So in other words, the probability of the patient being COVID positive, given that the test is positive, is equal to the probability that the test is positive, given that they're COVID positive is sensitivity, and then you multiply that by the probability of COVID, and you divide that by the probability of the total number of positives. So this looks an awful lot like the Bayes formula, and that's because it is. So this is a very practical day-to-day application of Bayes' theorem. And you thought you didn't know anything about Bayes' theorem. Okay, so I'll give you another example. So I think that repetition breeds familiarity. So I promise at the end of the example you'll feel maybe nauseous, maybe a little bit angry, but don't direct your anger towards me. It was Chris that asked me to do this presentation. You should be angry at him. But let's suppose that you're in front of a slot machine that is rumored to be lucky. It costs $1 to play. You can either lose $1 or you can win $2 for a net gain of $1. You play the slot machine 10 times. You pull it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you win 7 out of 10 times. What is the probability of winning for that slot machine? So one way to do it is pull it 1,000,000 times, and then you get a large sample size, and you can figure out what the true probability is. But without pulling it 1,000,000 times, what is the probability? So we can think a little bit about this. We know that the probability that it is probably around 0.7. 0.7 is going to be the probability that is most likely to produce the result that we observe. It might be 0.6. 60% chance of winning is pretty close to 70. Just by chance, you could get 70% out of it. It is much less likely to be 10%, but it is possible. So you know that it is a curve that peaks around 70% and tapers off from there on. But how do we figure out what the exact percentage is? We can do a simulation. So this is a uniform probability distribution. So you sample a number from 0 to 1, and the probability of picking any number from 0 to 1 is exactly the same. So let's sample from the distribution. Let's say we pick 0.1 randomly, and then use the 0.1 and put it into use that as the parameter for the binomial distribution. So binomial distribution is the probability of heads and tails. And then let's say you sample 10 times from the binomial distribution to simulate pulling the lever of the slot machine 10 times, and you get the result of 2. Well, the result of 2 doesn't match your empiric results. So let's just discard the observation then. So we try this again. We sample from the uniform probability distribution. Let's say we have 0.5. You plug that into the binomial distribution, and then you sample from the binomial distribution 10 times. And let's say you get 7 out of 10. Well, that's exactly what you've observed. So let's write that probability down, 0.5, in a piece of paper. And let's do that 10,000 times. Then you plot a histogram of everything in your piece of paper, and you might get something that looks like this. This is the result of 10,000 simulated flip coins, and it looks exactly what we would expect. It has a peak at 0.7, which is the probably most likely to result in our observation. It's called the maximum likelihood estimate, if you care. And it tapers off all the way up until 0, and it tapers all the way up to 1. So theory works. But wait a minute. So if the probability of winning is 70%, then you have a slot machine in a casino that makes you money. And it's all well and good in a theoretical situation. You're in physics class and they talk about a train going in a straight line from Toronto to London at 100 kilometers per hour. But there's a lot of assumptions they can't really have to suspend your disbelief, right? This is just a theoretical world that you're talking about. And the purpose is to gauge whether or not you've been listening in class. And but if this was the real world, it is very, very unlikely that a casino whose purpose is, again, to make money, would install a machine that in the long run makes them lose money. So we know that the probability of winning is probably less than 50%. And we know that the probability is probably like more than maybe 10%, because you also have to give the illusion of winning to the gambler. So the result of 70%, 0.7, doesn't seem right. It doesn't sit right with our understanding of the world. Our understanding of the world has very little to do with the numbers that we see, but but we have information from other realms that we can incorporate in our analysis to get a, a realer number, if that is even a word. Okay, I've talked about these before. I'll just mention them again because they're kind of important words to use. And so this slide is incredibly repetitive, but I think it's good to repeat important definitions over and over again. So the prior distribution is the probability distribution that reflects what you know about the real world. And the posterior distribution is the probability of observing the data based on on the prior distribution. The likelihood function is the data itself, and the maximum a posteriori, sorry, I should say a posteriori, is the maximum of the posterior distribution. So remember we talked about how we believe that the probability of winning is probably less than 50% and no, probably more than like 0.1 or 0.2. Well, we can draw that probability that probability distribution that we imagine in our heads. We can do this through a bit of a more formalized process. You can use like beta distribution, you can use a Gaussian distribution, yada, yada, yada. You can also use a crayon if you want, as long as it integrates to one. It is a probability density function. But this is going to be your prior belief about how the world truly works. So then you perform the exact same exercise as previously. Instead of using a uniform probability distribution where there's an equal probability of any number from 0 to 1, you use the prior probability, the prior distribution that I just described earlier. And then you do that 10,000 times, and then you plot the histogram, and you get this. So this is the posterior distribution that you would get if you use a prior that incorporates the knowledge that you're probably most likely to lose if you play at a casino. So this figure illustrates the impact of a prior. So this is a non-informative prior. This is not, I think this was an error by the paper. This is not a probability distribution, a probability density function, because there is a probability of 0 for everything. This just mathematically doesn't work. It has to integrate to 1. Anyway, so if you have a non-informative prior, then your posterior distribution is going to look just like your likelihood. If you have a weakly informative prior, then your posterior is going to be your likelihood distribution, but shifted slightly. If you have an informative prior, you're very, very certain that your data is going to be going to look a certain way, then you have a greater shift. So your prior distribution has and what it looks like, the shape, the accuracy is going to have a big impact on your interpretation of the empiric data. That is the posterior distribution. So that leaves us with the first case of Bayes formula in medical literature. So let's say that you have a neutral for atorvastatin, and you want to test this. You want to test atorvastatin on a patient population from a certain geography. So you kind of already know from a large body of data of how well atorvastatin is going to use, and then you can use that data to generate a Gaussian curve, like a normal distribution, and use that as your prior for your study. You can also use subjective priors based on your understanding of the world. So an example could be you're studying the effect of antibiotics for COVID-19. So if we know that antibiotics are probably not going to work for viral infections, so you're already very, very skeptical going into the study that it's going to work. So a spurious positive result would still have a lot of doubt based on your understanding of the human body, viruses, et cetera, et cetera. And sometimes it's a combination of both. A lot of papers will use different types of subjective priors. They'll use subjective priors that are optimistic and pessimistic and neutral. So this leaves us with a case number 2 of how Bayesian statistics is used in medical research. There's something called the Bayes factor function, also known as BFF. The BFF is the ratio of marginal likelihood of one hypothesis over another. The first hypothesis is the alternative hypothesis that your intervention is doing something. And the second hypothesis tends to be the null hypothesis where there is no difference. And the word here, the functional word here that should make this computation a little bit scary is the word marginal. It involves the marginal probability, which is very difficult to calculate to impossible to calculate. Even though the concept of the Bayes factor function is very simple, the implementation of the equation in real life is pretty involved. Sometimes you use Markov chain Monte Carlo methods to approximate the equation, and in special cases you can use algebraic equations to solve it. Won't really get into details on the calculation of k, mostly because I don't really understand it myself. But at the end of the calculation, you get something that is much more useful than the p-value. Because depending on what your k is, you can either be pretty certain that your alternative hypothesis is true, that your intervention is doing something, or you can be really, really, really sure that beyond a shadow of a doubt that it makes a big difference. And more importantly, not only do you, if there is no difference, not only do you have to accept the null hypothesis by default, if the k value is a certain fraction, if it is very, very small, then you actually have high confidence that the null hypothesis is true. And this is not the case with the t-test, where you get a p-value and that you accept the null hypothesis by default because you can't reject the null hypothesis, but you have no idea how confident you are that there is no difference. So the reason why I started to be interested in Bayesian statistics is because there is a new way that I heard about that you could estimate the area under the curve for vancomycin with only a trough. Traditionally, in pharmacokinetics class, we were taught, like, if you want to calculate the area of the curve, you do the peak and the trough, and then you calculate their pharmacokinetic parameters, and you plug it into an equation, and you get the area under the curve. But I heard that you could use Bayesian statistics, so I went into this journey to learn everything that I know now about Bayesian stats. And so I created this calculator. It's available at vanco.com if you want to use it. And it does make you curious about, why this calculator is Bayesian. What makes this calculator Bayesian, other than it sounding pretty fancy? What makes it Bayesian is that you have a level, but the level is not taken at face value. You have a trough, but you can extrapolate what the peak is going to be with prior information, about the patient's weight, their creatinine clearance, and population models that correlate patient weight with volume distribution and creatinine clearance with clearance of vanco. And with these priors, you can have a much higher certainty of estimates for the patient's PK parameters. And using these PK parameters, you can simulate the patient's response to various dosing measurements of vanco, and then you can target either troughs, or you can target AUC that way. So this is an example. So let's say you do a pre-fourth, like you're taught to, and let's say there's a pre-fourth of 10. So that sounds pretty good. And you have let's say you have a pre-fourth of 10, but the patient is obese and they have the creatinine clearance is okay. It's not great. Um, the reason why we pick pre-fourth is because we're generally taught that by the fourth dose you reach steady state. Well, reach steady state is it's not a function of how many doses you give. It's a function of the half-life in that particular patient. And the patient who has poor renal function, the patient who's older, the half-life is going to be longer, so the time steady state is going to be correspondingly longer. And in this case, as you can see, you have a pre-fourth of 10, and the Vanco level is going to continue to rise over time. But with a 20-year-old who's a little bit lighter and has normal creatinine, well, you've already reached steady state, even though the empiric data is the same. You have a pre-fourth that is 10 milligrams per liter, but depending on the prior information, on what you understand about the patient's body, it changes your interpretation of the empiric data. So in summary, Bayesian statistics is intuitive because it answers what we think our trial is meant to do. It answers the probability that a certain hypothesis is true. But it's also hard. It can be hard to implement, and it can be hard to understand because our formal education has not really prepared us to understand it. There are many implementation and use cases of Bayesian statistics. I've presented just a few of them. Bayesian statistics is very common, for instance, in artificial intelligence because it kind of gives common sense to artificial intelligence. So you might see something that is considered Bayesian, but it might not be clear what that has to do with priors and posterior and marginal distribution, et cetera, But that's just one use case of a very basic concept, just like how ANOVA test and chi-square test and t-test, they all have a same very remote root concept, but they're very, very different implementations of the system. And I hope that you come to appreciate that there is definitely pros to Bayesian stats. People don't use it just to be fancy. There are advantages of that method that frequentist statistics just cannot match. But conversely, there's times where frequentist stats is better than using Bayesian stats. You just have to look at your use case and look at your audience and see what's best. But they both have their place in literature. So I hope that most of you are still awake, and I thank you for attending my talk. If you have any questions, you can address them to Chris, and maybe he'll forward them to me. Maybe he won't. I think it'll probably depend how he feels. And best of luck with your residency, and best of luck with your career. I hope I see you guys sometime. Thank you. Bye-bye.